Hi, this is Dr. Harris with some notes about comments on some notes for sections 4.1 and 4.2 in Math 345 DE. Hope you're doing well. My apologies if you can hear my dog panting in the background. He's hungry, ready for dinner, I think. Anyway, I wanted to just touch on a few topics here while we're together from sections 4.1 and 4.2 of our DE textbook. And the first one is how we go about taking a differential equation or two or more differential equations and write them as a system of linear differential equations. So I'm asking you to read in the text to make sure you understand what we mean when we say system of linear differential equations. Hopefully we know what a linear differential equation is. A system is just going to be a collection of linear differential equations. So our first example asks us to look at x double prime plus 4x prime minus 5x equals e to the 2t and recast that as a system of differential equations. We've got a single linear differential equation. We actually would know how to solve this using undetermined coefficients, but we're going to look at just translating it into a system of DEs. And so the first comment I want to make is notice that I could, and I've got some reason to down below, to solve this DE for x double prime. And so x double prime would be equal to 5x minus 4x prime plus e to the 2t. So we'll keep that in mind for a minute. And then the idea is to let x1 be our variable x, and let's let x2 be x prime. And now if I differentiate both of these equations, I get that x prime is x1 prime, no shocker there, and x double prime is going to be equal to x2 prime. But just one more comment before we move on. Notice that from over here, if x prime is x2 and x prime is equal to x1 prime, then x1 prime must also be equal to x2. So to take a second to make sure that you're with me on where I'm getting this statement from. So we'll move down then, and this is actually going to be the first equation in my system. x1 prime is equal to x2. And then my second equation is going to be a statement about x2 prime. And since x double prime is equal to x2 prime, I can just replace this x double prime, up here with x2 prime. And so x2 prime is 5x minus 4x prime plus e to the 2x. But x was x1, x prime was x2, and so therefore I get x2 prime is equal to 5x1 minus 4x2 plus e to the 2t. So this is how we would translate this single second-order differential equation into a system of two first-order differential equations. The second example, we actually have two equations in two variables. We have equations in relating x prime plus 2y prime equals 2x, 4x prime minus y prime equals x plus 3y. And I want to write this as a system of linear differential equations. Essentially what we're going to do is we're just going to play a game of elimination, two different eliminations here. In some ways this isn't necessary, but to be consistent with the notation of the text, I'm going to say let's rename x as x1 and y as x2. And so therefore x1 prime will be x prime and x2 prime will be y prime. And we're just going to, as I said, perform two different eliminations. We want to get x prime related in terms of x and y prime related in terms of x and y. And so the first thing I'm going to do is I'm going to eliminate y prime. And I can do that by multiplying the second equation by 2. So I just copy the first equation over, x prime plus 2y prime equals 2x. And then I get 8x prime minus 2y prime equals 2x plus 6y. And now I can just add those two equations together and eliminate y prime, in which case I get 9x prime equals 4x plus 6y. Then I can multiply the first equation by -4 to eliminate x prime. And so I get, that's just taking the first equation multiply by -4, just copy down the second equation over, then combine the two, and I get -9y prime equals -7x plus 3y. I'll take my first equation divided by 9, take my second equation divided by -9, and I could leave it like this, and I've got my equations now written as a system of differential equations in which only one derivative appears, or I can translate them over, replace my x's with x1s and my y's with x2s. So here are two examples of rewriting equations that aren't written as a linear system of differential equations as that. Next, I'm going to move on into section 2 of chapter 4 and pick out a couple of the topics that are there. And hopefully in coming sections, we'll see why these are important ideas. So the first one I want to talk about is what it means to be a set of vectors means to be linearly independent. And in the text, I believe we see the definition is that a set of vectors will be linearly independent. We're talking about a set of row vectors or a set of column vectors here. If the only way I can take sums of constant multiples of those vectors and get the zero vector out is for each of the constants in front to itself be zero. Certainly, if I do replace C1, C2, C3, etc. up to Cn with zeros, I will get the zero vector because each of these is the zero vector from scalar multiplication. But we want to know is that the only way I can get the zero vector out by taking sums of constant multiples of these vectors? Well, we're going to look at two examples and see one case where we have a linearly independent set, one where we don't. And in both cases, we're going to actually solve a system of equations. So my first example is to show that the set of column vectors 1, 0, 0, 1, 1, 0, and 1, 1, 1, that set is linearly independent. So let's suppose that I have constants C1, C2, and C3, so that C1 times the first vector plus C2 times the second plus C3 times the third gives me the zero vector. Then if I do scalar multiplication, addition of vectors, I'll get the system of equations C1 plus C2 plus C3 equals 0, C2 plus C3 equals 0, C3 equals 0. Well, immediately from the third equation, I know that C3 has to be 0. And when I substitute that in here and put a 0 here, I get that C2 has to be 0. And then finally, if C2 and C3 are both 0, then C1 is going to have to be 0. So therefore, the only way I can get the zero vector out from combining these vectors is to take a zero multiple of all three of them. So that means that the set is linearly independent. My second example is a set of vectors that is not linearly independent. So again, let's suppose that C1 times this vector plus C2 times this vector plus C3 times this vector is the zero vector. I get this system of equations down here, and I'm just going to do a couple of eliminations. So if I subtract the second equation from the first, I'll eliminate C1, in which case I'll get 3C2 plus C2, gives me 4C2, and then minus C3 minus 3C3 minus 4C3 equals 0. So if I subtract equation 2 from equation 1, I'll get 4C2 minus 4C3 equals 0. Then if I multiply the third equation by 1/2 and then subtract it from the first equation, this should be a 1, by the way. This should be a 1 and this should be a 3. I didn't catch that error. So I've got 2C1 plus 4C3 equals 0. So when I do that subtraction, take 1/2 of this and subtract it, that goes away. I'm subtracting 0 from this, so I'm going to get 3C2. And then if I take half of this, I've got 2C3, and if I subtract that, I'll get minus 3C3. So then I'll get 3C2 minus 3C3 equals 0. I can take this equation divided by 4, take this equation divided by 3. In both of cases, then I get C2 minus C3 equals 0, or C2 equals C3. So as long as C2 and C3 are the same number, both of these equations are going to be true. So therefore, I'll take C2 to be any non-zero number, then C3 will be that same number. The easiest thing to do probably is to let them both be 1. And then when I pop 1 in to this equation, into C2 in this equation, and C3, put 1 in for both of these, then I get C1 plus 3 minus 1 equals 0, which means that C1 is negative 2. And so let me take that combination then. Negative 2 times the first vector plus 1 times the second vector plus 1 times the third vector does indeed give me the 0 vector out. So in this case, I found that there is a non-zero collection of constants that I can put in front of these 3 vectors to get the 0 vector, which means they are not linearly independent. And in a course like linear algebra, you would say that they're linearly dependent. This is going to come up in the next section. So we want to hold on to this idea of what it means for a set of vectors to be linearly independent. The last topic I want to hit on has to do with eigenvalues and eigenvectors. So we necessarily have a square matrix in this case, and our definition for these two terms, let's suppose that U is a vector such that if I multiply, so U is going to be, in this case, going to be a column vector. So U is a column vector such that A times U, we do that matrix multiplication, equals lambda times U for some scalar lambda. Then we call U an eigenvector of the matrix A, and lambda is its associated eigenvalue. So again, U is a column vector. And so as an example, we're going to let A be the matrix negative 2, 7, 1, 4. And I'm going to show you that the column vector U equals 1, 1 is an eigenvector of this matrix with associated eigenvalue 5. And the way we do that is I just perform the matrix multiplication AU, and then I'll take the scalar multiplication lambda U, and I'll show that I get the same thing. So if I take A times U, I'm looking at negative 2, 7, 1, 4 times the column vector 1, 1. From your review of matrix multiplication, we know that that's going to be negative 2 plus 7 in my top entry, and then 1 plus 4 for my bottom entry. Do those additions, I get 5, 5. But that's exactly what I get when I multiply U by the scalar 5. So since I get 5, 5 in both cases, that means that indeed 1, 1 is an eigenvector for this matrix A with associated eigenvalue 5. In the next section, section 4.3, we will talk about how to find systematically eigenvalue-eigenvector pairs. And then finally, just one last little brief bit on making sure that we recognize that we can write systems of linear DEs in matrix form. So if I've got a homogeneous system like the one we just discussed, or it's related to the matrix we just discussed above, x1 prime equals minus 2x plus 7x2, x2 prime equals x1 plus 4x2. Notice I can write this in this form, where if I did this matrix multiplication, I would indeed get these two expressions here. And so if I call x the column vector x1, x2, then x prime is going to be the column vector x1 prime, x2 prime. I get the system x prime equals negative 2, 7, 1, 4, x. Here's a non-homogeneous example. This goes back to the very first thing we talked about on the first page of this document. I've got this system of equations here. If I want to write this in matrix form, I would get x1 prime, x2 prime equals, and then I've got a 0 here because there's no x1 term, so I can think about it as 0, x1, 0, 1, 5, negative 4, x1, x2, plus the column vector 0, e to the 2t. And this would be its form if I wanted to write it in terms of vectors x prime and x.